How we can convert them from? Yeah, see, we looked at, I only like the website was there. That county, we never find anything. Good. Oh. Sure.
It looks like we're there, gentlemen. Well, welcome back. Looks like it's just us today. Hopefully we get some more people through Zoom, but if not, then we'll still have a time. Any questions at the moment to start us out? Okay, well, the rundown of the announcements are, we have our second exam coming up next Tuesday. So that's all we're going to do next Tuesday, pretty much, just work on the exam. And it's going to start in section 1819. This is chapter 1 stuff, but all about linear transformation, so it goes together. 212223, this is all about matrix operations, matrix multiplications, matrix inverses. And then 313233, they go together. So it's exams kind of in thirds in a certain sense. This is all about determinants, more about determinants, and even more about determinants, Cramer's rule, in 3.3. Really, that's going to be kind of a small contribution on the second exam. I think it's kind of a stretch to even write 2 questions on Cramer's rule, because we just really focused on one real concept there. So it'll be 1 or 2 questions, same as the kind of things that we did in our actual section 3.3. So that's our announcement so far. It's next, we're going to have to get through section 4.1, but we're nearly there. Our next topic is about subspaces. And after we get through that, linear algebra starts to get a little bit more common to like what we were doing in, say, chapters 1, chapter 2. This one is just one of those really abstract sections that comes around once in a while, then we move through it. But any questions or comments at all, folks, before we get started in 4.1 again? We don't have a review, but what we do have is the sample exam 2 problems are contained right here. These are the old problems. So they go from every single section and they've had all the notes taken out, all the formulas and theorems and things like that. So this is essentially, I'd say, the second best review document you could go through. We don't have an official review, but these things are posted. Probably the better review is your actual homework assignments that you solved amongst all these sections. Those are probably the better problems for the sake of review. Taking another look at them could be helpful, or just focusing on the ones you might have missed a point here or there. And then the second thing you can do for review is this one right here is a review for the whole course. So you could just go from sections 1.8 to 3.3. There's solutions posted at the very end of that as well. And that makes up a pretty well-rounded review in a certain sense. Unfortunately, we don't have enough time in the schedule for an actual review day. But because of that, I give lots of extra stuff like this. And you usually have a pretty strong expectation of what's really on the exam. It'll be kind of similar to how exam 1 was done. Any other questions about exam 1, or excuse me, exam 2 or otherwise? Okay, well, let's now take a look at section 4.1. In section 4.1, we reviewed what a vector space is. It's a pretty abstract object. But the good news is everything we did in chapter 1 followed all of this. And the reason this is such an important concept is if you can come up with some kind of set, V of objects, endow it with a couple operations. Maybe one of the operations is a type of addition, another one's a type of multiplication. Then if everything falls into just right, if it satisfies all 10 axioms right here, you have an honest to goodness vector space, and every single piece of theorem or development we do on vector spaces applies to your model. So that's the major idea of modern mathematics. They come up with systems of axioms, and anyone who has a set that follows that set of axioms instantly has like hundreds of different results that would follow for what you're working on. So after thinking about vector spaces, we're going to turn to a new concept called a subspace. In my opinion, this is where it starts to get a little bit more tricky. The idea with a subspace is, first, we have to have a non-empty subset of H. Non-empty makes sense. We have to have something in the set, or any mathematical knowledge that pertains to the empty set doesn't do us any good. There's no applications to the empty set. There has to be something in it. But even before that, the difficulty with this theorem is right where it says subset. We're really using set theory in a strong sense here, and so we're subsetting when we talk about a subspace. Let's just do a really quick example when we say subset, just to get a feel for that. You can just write down a couple really fast sets. Let's say for a set A, it's 1, 3, 5. For set B, it's 1 and 2. And I have to change our heart here. Let's add a little bit more space. And for set C, we have 3, 5, and 7. So our book doesn't use any special symbol for the word subset. But if you worked with sets before, you could use this symbol here to denote a subset. I'll go with how the author does and just write it out verbally. So looking at the 3 different sets, any volunteers for which set might be a subset of another in this list of 3 different sets? Let's take a look. Almost. It has one in common, but you're thinking along the right lines. When you think of subset, we're just seeing if every element inside B also belongs to A. But because of the 2, we can say B, right, is not a subset of A. Well, what did I do here? I don't seem to have any subset here of anything, but let's put down another one just to kind of fix that conundrum. Let's say C equals, how about 5 and 7? Those are some weird sets. We go and throw it down another one just to make the problem look a little bit more interesting. Well, 5 and 7, C is not a subset of A because 7 doesn't belong to it. Definitely it's not a subset of B. None of the elements are in common. But 5 and 7 are common to the set C, so we can say C is a subset of that set A. So that's what we mean by subset. Every element in the smaller set has to be a member of, oh, I said A, the larger set, which was C on this one. Let me fix that there. So that's the first issue about talking about a subspace of a vector space of B. We have to have an honest subset to start. So every element of H is contained in that larger space V itself. Well, as far as linear algebra goes, you could say, for example, if you take a vector, say U equals 1, 3, you could span that vector. So let's say H equals the span of that single vector 1, 3. Visualizing that thing, it would look like this. We'll go 1 up 3. So there's the vector. But if you span it, it includes every single multiple. It would also include the 0 vector through here. And it would just be a line in the plane. The plane itself is R2. But that would be the set V, the larger set, when we read this definition. So R2 is the larger space. And H, which is just the span of one single vector, that turns out to be an actual subset. And this is what the subset would look like in this kind of context. So we're interested in those types of sets, but this is just to get the conversation started when we talk about subset. So with that out of the way, let's read through the definition in full. A non-empty subset H of a vector space V will be called a subspace of V, provided we meet 3 different conditions. Now, this one's kind of redundant, but it's really important. It helps us resolve why we don't necessarily focus on the non-empty part of the set H, because we know that we're looking for the 0 vector to belong inside of it in the first place. So if the 0 vector of that vector space V is in H, then it's automatically a non-empty subset. It's got something, at least, a 0 vector. Say, for example, that one right there is non-empty. It does contain a 0 vector. The next operations are closure properties, the same exact closure properties of having an honest vector space like V. What this all entails is when we say H is a subspace of V, H is also a vector space in its own right because it will satisfy the closure properties. We're using the same operations of addition, vector addition, and scalar multiplication as the subspace V. And so that means all of these properties ought to hold except the closure ones. The closure property here and here, those are the ones that can fail and make something, even though it's a subset, become not an actual subspace, and so not a vector space at all. There's a lot of things to consider with this definition, and it's kind of a hard one to unpack. We mentioned it's similar to something else, so let's take a look at that. In section 1.8, we had the definition of linearity. These are not closure properties, but they're very similar in a certain sense. We call these operation preserving properties. On the left, we were doing vector addition in the domain space. On the right, we're doing vector addition in the codomain space. And same kind of ideas with scalar multiplication. Back to subsetting, it feels familiar, but the questions are a little bit different. It's more about not u plus v being operation preserving. It's about u plus v still being inside that space H. We cannot leave it. So we have to show this is true, u plus v is in H, and we have to show this is true, c times u is in H. And this has to qualify for any two pair of vectors, u and v. So this must work in full generality. We can't use a counterexample. And same for here and here. Part C has to work for every single vector u and every single scalar r. So if we're trying to show something is a subspace, we can't define these vectors. We have to let them be whatever they could be, unless your set has just one vector, then, well, that doesn't give us a whole lot of options. So I started example 5 because this space right here actually has a name. This is called the trivial subspace. It might remind you of the word trivial solution. That's just referring to the zero vector. This is the trivial subspace because it's a space with exactly one element, just the zero vector. It's a zero vector with two elements, so it's right to ask if it's a subspace of R2, but if you were asked if it's a subspace of R3, it's an automatic no. The entries right here don't actually even live inside there. They're not even a subspace, a subset in the first place. Well, that's the idea with the definition. We'll walk through this definition several times just to get a feel for it. But any questions first, folks, before we try it out on that example? Okay, let's give it a start. It's a very tricky kind of set of definitions to work with. And following the color coding is my way of conveying what makes it tricky. On part A, it says the zero vector of V is in H. That means we start part A by doing the following. Let this thing, which would be equal to 0, 0, be the zero vector of V, which in this problem would be the larger space R2 right here. So that's the zero vector of R2. And what it says is, once you've indicated that zero vector, you have to show that it's inside the set H. That's not so bad. The set H contains only that one vector, so it's automatic. This problem, again, is more about just studying the definition. We can say, then, that zero vector is in H. So H has the possibility of actually being a real subspace, meaning it's a vector space in its own right, even though there's nothing too interesting going on there. It's just the zero vector. Any questions, folks, with part A?
So in this case, that is zero vector subspace of all the vectors?
Absolutely. So any vector space you indicate, let's say, for example, let's go to one of those weirder ones, like a function space, say, let me see, where am I at? There we are. At the function space CAB, which is a set of all continuous functions, an automatic subspace would be this one. Put in the zero function, we indicate it just by Z, and it is a subspace of CAB immediately. The challenge with these kind of vector spaces and subspaces is if it was a little bit more involved, if this was a larger set of functions, then we would have to write down the zero vector and show that that really truly belongs to that subset. So sometimes just writing down the zero vector is a challenge because it can look a lot different versus, say, a function space. This one's a polynomial space, but still a function space, just specific functions. Or if you're working in, say, Rn, now you have a different kind of zero vector. But other questions about that so far? Okay, so every vector space will have a trivial subspace formed by putting in whatever that zero vector happened to be inside that set. And now to continue through the verification, here's how the next part goes. Part A is different than part B. In part A, you grab something out of the larger space V. But in part B, you're staying within the set H this time. So we will grab two vectors UV in H. Well, that's weird to say, right? Because there is only one vector in H. But if you see things indicated as UV, this is just our way of saying U and V are allowed to be different, but they can also be the same. Nothing prevents it. There's no exception there. So we can work through part B by saying, let U, comma V, be in H. Now we're just using set theory in full. Because they're in H, they are both equal to the zero vector. We can say then U equals V equals that zero vector there. This doesn't finish off part B because this is what we have to show. We have to show that U plus V is still in H. And I feel like this color coding could be improved. Let me fix that here and here. Sorry for any confusion with that color. So let's just add these two vectors together. Shouldn't be hard, right? They're both a zero vector, but this is what the motions would look like. Let's write next. U plus V, that's just going to be the zero vector plus the zero vector. We happen to know adding the zero vector to itself returns the zero vector. What do we have to say? That it is in H. Really fast check. Yep, it's still there. That's still just the zero vector. So we'll say is in H. So that finishes off part B. And that was so fun. We'll just redo it. Same kind of argument, part C. All we change to now for part C is, well, we have to grab a couple things. We need a vector U coming from H, and we need an arbitrary scalar C from R. So to start out, let's say, let U be in H, let C be in R. So now the argument can start. We have our two objects we need. And this is all we have to show. The scalar multiplication of whatever that scalar is, it can be anything, times U have to still be in H. It's a foregone conclusion, right? But here's what the motions look like. We'll say next, C times U is going to equal C times the zero vector. And we could add some steps here to clarify what's going to happen. This is C times 0, 0. Rescaling the zero vector just means you're taking C times 0 in all the entries. But then 0 takes over. We're just wiping everything out, getting the zero vector back. And it is in H. So we did it, folks. This is all 3 steps. But what's tricky about all this is we have to show our conclusions so that I know that you know what the conclusions were at each step. There's a conclusion of part A, that the zero vector is in H. There's a conclusion of part B, that U plus V is in H, really conveying this part as the major thing we want to take away. And there's a major conclusion here that C times U is in H. And there's yet one more conclusion we still haven't written down. Anyone spot the last statement we ought to make? It's honestly pretty subtle, right?
Subspace.
Exactly. We were setting out to show H is a subspace of R2. We have 3 different things that fell into place, so we need to assert once and for all. This shows H is a subspace of, I'll write this again as V, just to be specific with the original definition, since we're trying to track it carefully. It's a subspace of V, which is equal to R2. So we did it, folks. The conclusions are really kind of easy to miss on this. And that means grading these can be kind of tricky sometimes. If you had a couple missteps and maybe lost a bunch of points, I am giving opportunities to rewrite your section 4.1 problems, the things that you missed, because this is pretty tough to know what's expected for these kinds of arguments. There might be a couple attempts that you have to make, and that's kind of normal, I'd say, learning this stuff. But any questions at all, folks? Tracking through the definition? Okay, so this is what a subspace would look like. This one's a little bit weird, so we're going to start building on that, looking at more and more interesting subspaces and vector spaces. And on the next one, if I recall correctly, this would be a vector space that we've looked at, but haven't really worked with too much directly. This space. I mean, I guess we have. We've done determinants, we've done matrix inversions, and that's all done in this space right here, the space of square n by n matrices. So let's take a look at what's going on in this one. I've reduplicated the definition because, again, it's a pretty tricky one. We're trying to track it carefully to learn it. Starts off by saying, let the set H here be the set of all matrices now. These are going to be regarded as vectors if we can show it's a vector space. There are square matrices, and it has a non-zero determinant. I mean, that's a nice set, right? That means H is officially the set of all invertible matrices. It's a wonderful algebraic object. We use these things all the time. And it asks us, is H a subspace of Rn by n? So the question is about H. The larger space, the V space, is Rn by n. And here's where we have to start. If it is a subspace, we need to show that the zero vector of V, that set right there, lives inside H, this set right here. So that's the challenge. We have to now write down the zero vector. So let's show in part A and write the zero vector of V equals R n by n. And it is okay to say zero vector here because that truly is now a vector space in its own right. In section 2.1, we defined matrix addition. That's equivalent to vector addition and the scalar multiplication as well. So let's write it down. I'll write a capital Z because our objects inside Rn by n are matrices. We usually use capital letters and Z to denote it's the zero vector. But what would it look like? Well, it's got to have n rows and n columns, all of which are zero. Let's see, how could we write that down without too many steps? You could just kind of go like this. And essentially everyone's going to assume you mean everything there is zero. Or you could be really specific by writing out, this is n columns, n entries per column, all zero. Zero as in the actual real number zero itself. So there it is, that's the zero vector. We have to show it's inside H, but that means we're also using set theory at the same time. How do you get inside H is always a question you should ask yourself. H is a set of all square matrices A of size n by n, such that the determinant of that is not zero. That's how you get in. So if the zero vector is really inside Rn by n, we have to show that a determinant of it is non-zero. That's a problem, right? If you go and calculate determinant Z, well, you have a lot of great options, right? I'll do a cofactor expansion across row one. You're just producing a whole bunch of zeros. The whole thing is zero, but that means we can't get inside H. Let's say right away, this shows Z, the zero vector of the actual vector space, Rn by n, is not in H. That deserves an exclamation mark because that means there's nothing further to do. The moment one property fails, and oftentimes that's the easiest one to check, everything has fallen apart. There is no possibility H could ever be a subspace. In fact, it's not even a vector space, not with the operations we're used to using. So we'll say here for our conclusion, this shows H is not a subspace of B equals R n by n. So again, I think the big takeaway with this is you don't have to verify every single condition. If you suspect one fails, just argue this way, show that it fails, and all of your work is done. It's irrelevant now if this even works or if that works. Well, any questions, folks, with getting through part A, or example 6 rather? Okay, I think for me personally, these are definitely pretty weird arguments because it's all about working through the set theory right here. And that means some of the work that the author indicates is a little bit tricky. He doesn't always necessarily indicate a set. He says it verbally, but he doesn't write it down. It's up to us to know what would the set look like based off his verbal description when you read the exercise sets. So let's give that a try very next. I think that's the next one here. If that would be one of those kind of problems, this would be an easier problem in example 7 if H was just written out as a set and we could observe it. But it wasn't done, it's just indicated verbally. So let's do the first step of writing out H this way. H is going to be equal to, it's the set of all polynomials of degree at most 3. So we can say, set of all polynomials, I'll just call it P. You could write P of T, but it's often just indicated as P. That's the name of the function, and we're not trying to evaluate it. But here we can say, because it's polynomials of degrees at most 3, all the polynomials come from P3. In other words, it's a subset. And we can say right here, P in P3, then the colon to say such that P of T equals, now we can indicate the function. It would be something along these lines. Degree at most 3 means there's an A3 coefficient, T to the power 3, A2 times T to the power 2, A1 times T plus A naught. We'll say next, well, what was special about this? The integers were, well, let me say it better, the coefficients were integers with integer coefficients. So let's say down below, or right down over here, where A3, A2, A1, A naught are in, and here's a new symbol, not sure if we used it before, but it's in this set, Z. Z is the way we indicate the set of all integers. And I believe it comes from the German word for integer or number. So if you ever see that symbol, it's written out this way as a set. So there it is, our set of all integers. We have a polynomial space here, well, a polynomial subset, where all the coefficients happen to be integers. So think like 5, 0, -12, maybe 10, but there's no possibility that that could be square root of 2 or pi or anything along those lines. So that's our set. It's a very interesting set. It has a lot of rich algebra that goes along with it. And now we wonder, is it a vector subspace of P3? If it is, that would be fantastic. But I would say this one's not. This set is really highly specific. The moment you set integer coefficients, something has to go wrong here, and it's our job to spot it. Well, let's take a look through the definitions. We're thinking of H and V in this way. When it indicates V, they're talking about the larger space, P3. So let's write that as equals V. And now if you think about the 0 vector, well, the 0 vector of V looks like this. So the 0 vector of P3, which is equal to V, the larger space, is Z of T, identically equal to 0. There's really only one coefficient in a certain sense. We're thinking of that as a coefficient as well, even though it's just the constant term. But that's an integer, so it does actually belong to the set H. We'll say here, since there are no non-integer coefficients, that function z is an h. And that's kind of unfortunate. It means, well, we were following our nose, trying to out the zero vector. That's still oftentimes the best approach. It's usually pretty fast to show that fails, if it fails. But this time it didn't. Part A is actually true for this set. So we might think, maybe part B is true. It actually is. And we might not actually want to show it because I would suspect part C is true, or excuse me, false. What we really should have done is go directly to part C and argue that that one has no closure property whatsoever. But why is this one true? Well, if you grab two polynomials and they had integer coefficients, add an integer with an integer, and you still get an integer. So the sum of two polynomials has integer coefficients, it's back in H. But I suspect this one's going to fail very, very easily. So let's go now to part C and make that happen. But we're trying to show part C fails. We are looking for a counterexample, much like we've done in prior work. Let's indicate that here. We want a counterexample. The reason we want one is we're trying to show that this property does not, in fact, work for all vectors u and h, all scalars c and r. Let's start by just grabbing a vector in h. So we're doing this part. We wouldn't call it u. That's what's kind of tricky about the definitions. This is just generic to any vector space, but ours is specific. It's a polynomial space. So let's call that object, how about p or q, something that's more familiar. Let p of t equal, it's a counterexample, so we want a specific polynomial. And you know what? That's pretty specific, 2 times t. Or it could have just been t itself. I just wanted to exhibit the coefficient a little bit clearer. It has an integer coefficient. Its degree is below 3, so it does belong to h. We need to say that here. Then p is in h. Now we're trying to leave this set. We're trying to show closure fails. And the only way we're going to do that is we pick our scalar c here very wisely. So let's let c equal, and any volunteers for a good choice of a scalar to break part C? Kind of tricky in a way. And what makes it tricky is it's a set theory problem. So we have to think in terms of what was the set and what are we trying to show? We're trying to show c times u, or c times p in this case, is not in H. So I'll just put an X there to kind of signify that. So now we have to ask ourselves the question of, how do you get inside H? You get inside H this way. Your function has to look like this, where all those are integers. Now, if it's 2t, we chose that to be 0, 0, a 2, and a 0 right there. So we placed a 2 in that location, and 2 is in z. It's an ordinary integer. But now, if you do something like this, let's pick our favorite irrational number. I kind of like e for Euler's number. That's a nice one, about 2.71. That is not rational. So if you let c be e, then c times p, it's a function operation, so we wrap that whole name, c times p, with parentheses, evaluate it at t, is going to be equal to c times p of t. C is equal to e times p of t, over here is a 2t, which is equal to twice e t. Now what's the problem? 2 times e is irrational, just like e is an irrational number, does not belong to the set of integers. That means we're not in the set any longer. We left the set the moment we multiplied by any irrational number. Could have been root 2, it could have been a custom irrational number, maybe pi or something. But we have to say here, why did it leave H? Since 2e is not an integer, c times p is not in H. That's pretty much all we need to say from the very beginning. We broke closure right here. You don't necessarily have to make this statement, H is not closed under scalar multiplication, because you already just showed it right here. It would almost be redundant. The last conclusion we have to make is that set H, as interesting as it is and rich with structure, it's just not a subspace of P3. It's not a vector space in its own right. You'd have to define a whole new set of operations. So here's our end conclusion. This shows H is not a subspace of the larger space, V, which was P3. So we did, folks. We showed that that cannot possibly work for our particular set. And so that's our end conclusion down below. Any questions at all, folks, on getting through that one? Okay, definitely wild stuff. And if you felt like this was a pretty confusing example, you're not alone. The first time I learned this kind of subject, I felt like I had to read section 4.1 a lot. So I put here, try reading it at least twice. It actually helps. You're reading it once just to get your brain familiar with the terms and all the things that are weird. Read it a second time and your brain has a lot more traction on every single thing that's weird about it. And then these kind of problems start to make a lot more sense, particularly in the homework. So let's try another one. These are not easy problems, so I felt like doing this subject in 2 days, lots of examples along these lines is what it takes, because they are very different from problem to problem, even if we're still in a polynomial space, P2 this time. Let's try out this one, see how it goes. It says, let H be the set of all polynomials in P2 that have exactly one real root. Now, that one's a hard one to write down as an actual set. So I'm going to leave it just like this, indicated verbally, but let's still try to visualize it. If I can't write a set down in a nice way that's helpful, we can at least plot this thing. They're polynomials, so we can plot them in a t and y equals p of t kind of space. It says it has exactly one real root. And so if I plot something that goes like this, this one is not in H. It doesn't have exactly one real root. It would have two roots, one right here and one right here. So this one is prohibited from being in the right space, even though it does look like it would have been of degree 2. If we draw one that goes like this, this one is in the set. I mean, this one is going to be degree 1, so it's linear. It kind of feels weird even when we're thinking polynomial space. It includes the constant functions, the linear functions. And this one does have exactly one real root. So this one is in H. So those are the kinds of functions we want in H. The things that intersect once, not necessarily at 0, but just to have exactly one real root. So for just one additional example, this polynomial, this one looks like a degree 2. This one is also in H. It has a root right here, exactly one of them. So now we have a visualization of what this set looks like. Yes, go ahead. Let me see exactly what.
In that you don't, in that you want just excuse me, one intersection across the t-axis.
Let me think about
Sorry, I
that.
don't know if that's-
Well, onto would be more like along the lines of what's happening with this function right here, because every single value on the y-axis is obtained by some input on the t-axis. So onto means your entire codomain, this time the y-axis, can be accessed by some point on the domain itself. For example, over here, we would just have to put in a point going this way, kind of misconfigured it, going that way to show it. Does that make sense for that question there? Awesome. And that's a good question as well. You could rewrite this whole thing to say H is a set of all polynomials that are on two as functions and ask the same kind of question. Is that going to be a subspace or not? I think it actually would be. We'd have to go through the actual arguments to show it, but set of onto polynomials, that sounds like a vector space in its own right. Other questions or comments so far? Okay, well, we've got what the set looks like. Now we have to decide, is it a vector space or not? Or a subspace of P2? So this set H, oh, let me not change the color coding. Let's keep that consistent in the notes. H is going to take the role here. And if we think it is a subspace of V, V is going to be the set of all polynomials in P2, then part A ought to hold. So let's show if that's true and then work through the rest. Well, the first thing you have to do in part A is actually write down that zero function. Here's how it goes. Set of all polynomials in P2 is the space V, and we can say the zero vector in P2 is, now we have two ways to write down the zero vector. The first way is a huge shorthand, and it's pretty valuable. It looks like this. Z of t identically equal to 0. So that's the zero function, which would be the zero vector of P2. If you wrote it down this way, we're actually kind of hiding some information there. Let's actually do the expanded version. That is Z of t equals 0 for all t in R. This is the second way we wrote down the zero vector, whether it was for a polynomial space or the space of continuous functions, CAB. But notice what we just said here. We have a 0, and that's for all t. That means we have violated this terribly. There's not exactly one real root of the zero function. There are infinitely many real roots of the zero function right there. In fact, if you were to plot it, it looks like this. It's kind of hard to plot. Let me try to do it differently. Let's just bump that pen up. Here's the plot of the zero function. And it's intersected the t-axis infinitely many times. That tells us immediately then, well, the zero function right here does not qualify for that statement. And so it's not an H. We show that this is false right here. Let's say this shows Z is not in H because it has infinitely many real roots. We say real roots to essentially mean x-intercepts. We're trying to avoid complex valued roots. Well, any questions, folks, on the run through for this one? Okay, these arguments, again, they're pretty tricky because when you look at this definition, there is a lot of stuff happening. There is a set, there is a subset, and the way they interact depends on what part you're looking at. So the thought was, you had to grab the zero vector for V. There it was. You had to show it's inside the set H, which means it has to qualify that set membership condition, but it failed. So we said it's not an H. And now we have to give one overall conclusion. What all this shows is H, as interesting as it is not a subspace of P2. So that's our final statement on this problem. Let's say down below, H is not, let me write out slightly differently, didn't mean to scribble, let me fix that. H is not a subset of V, which is P2 in this problem. So that's another one down, and if you're like me, you probably still feel these are pretty tricky. Let's try another one along these lines just to see how the next one could go. Any questions at all, folks, at the moment? Okay, so here's example 9. Another polynomial type space because it's take some work to get a feel for these, and there's a few of these in the homework set as well. So I felt like we should do a good number ourselves. And here's how this one goes. H is a set of polynomials in Pn such that P at 0 evaluates to a 0. So it's not saying it has a certain number of roots. What it's saying is 0 itself is a real root to all those functions. This is not a bad one to rewrite out. Let's say, using set theory language or symbols, H is a set of all polynomials P in Pn such that all it has to qualify for to get inside H is put in the value of 0 and you get a 0. So now if we look at the graph above for just a moment, this polynomial would not have qualified, but this one would have, because at 0, it evaluates to 0. Well, we want to show if H is a subspace of Pn. This time n is not even specified. Well, let's give it a try. It turns out this one is a subspace. That's unfortunate in a way, because if it is a subspace, you have to show all parts, verify them as true. So again, this is probably a good one to just get used to the definition as well. Let's color code this up. It's definitely a non-empty subset. You can write P of t equals t, and it's automatically in this function to satisfy that condition. Next thing we have to take a look at is, in part A, we have to grab the 0 vector of v to start. Let's write that out. Let z be the 0 vector of v equals Pn. Then, well, what do we know about the 0 vector? Z of t will be 0 for all t in R. That's just us defining the 0 vector. Next thing we have to show is that 0 vector is in the set H. That means we have to now take a look at the set theory angle and look at that condition for set membership. It's automatic, right? That's kind of nice. We have a 0 vector. We can say z, let's say it this way maybe, since z at, we need to evaluate at 0 to show this. Z at 0 evaluates to 0. Z is in H. So we just showed that part right there. We have to grab the 0 vector, then exhibit that the 0 vector qualifies for set membership. Then we have to make a conclusion. The 0 vector is in that set. How do folks feel about part A? Does that make sense on that one? Okay, lots of jumping through loops and hoops, and if you put like an arrow system on this process, connecting how we went through all that, it's kind of getting convoluted. But again, that's what makes this kind of a hard set of definitions, and that's why we're practicing lots of examples on it. So part A qualifies. Let's now go to part B. And in part B, we have to start with 2 arbitrary vectors inside H. I wouldn't call them U and V like we mentioned before, and I probably wouldn't call it P either, because if you call it P and Q for your 2 polynomials, P might conflict with what's written here. It's a stylistic choice, but I'd say it's a good idea to start by writing let, it's not P and Q, let's go for Q, comma R, be in H. So now that we have 2 things in H, it has to satisfy this condition. So let's just say it right here. So we're looking at it. Then Q at 0 equals 0 and P of 0 equals 0. Only circling it to show that's the set membership. If we asserted it came from H, those are properties we have just automatically. So next step, we have to show the sum of those 2 vectors is in H. That'll be the closure property. So we go down below and write out Q plus R, except these are functions now. So we'll use a function operation. Q plus R at T is what we really need to evaluate. This next step is, again, just purely a function operation. The way this vector addition is defined in a function space is we take Q of t plus R of t. But all the way back in college algebra, that's exactly how we define it as well. It is kind of curious that in college algebra, these definitions were defined in a way with linear algebra actually in mind. It's just that we probably were not connecting the thoughts back in the day studying that topic. So we have Q of t plus R of t. And you know what? I did make a mistake here. This is nice and okay, but does it really help us? Not a whole lot. Because we're trying to show Q plus R at 0 satisfies that it equals 0. That might help, but let's backtrack a bit. It's always good to look at what you're trying to show. We need to throw a 0 in there to be specific. And write out that this is Q of 0 plus R of 0. All because of that condition there. That was a required step at this stage. But once we're here, well, we know what Q of 0 is. It's 0. We wrote down what it meant for R to be an H. R of 0 is also 0. And sorry about that. That was Q and R. I think I was still thinking about polynomials P at that moment. So that's 0 plus 0, which is equal to 0. And we've connected this end to this end. The function that's right here is Q plus R. So we need to assert this shows Q plus R is in H. Now that we've done that, there's our part B. It's now qualified. Any questions, folks, with running through part B? Okay, well, we're almost there. It'd be tragic if this one fails, but because of that 0 right there, we're just going to rescale this polynomial. It's a glorified C times 0. It looks like part B or C should work as well, but knowing it should work or feeling intuitively like it ought to work is never good enough in mathematics. There were plenty of things that people thought were true, but when they looked at it and tried to verify things, a whole bunch of results were false, and there had to be a lot of corrections back in the 1800s. But let's take a look for part C. We'll start off by saying U is in H essentially, which would mean for us, let Q be in H so that Q at 0 is 0. Again, just circling these to convey the set membership condition. Next, we have to pick an arbitrarily scalar C in R. Let's say let C be an R. Now we can't pick a specific C like pi or E like we did before, because now we're trying to show this works for all C. A counterexample is not going to help us. Next thing we'll do is this portion, C times U. Let's say then C times Q in this problem. Now let's be careful. We don't want to evaluate it at T. We want to evaluate at 0 and show that the output is 0. So C times Q at 0 would become C times Q at 0. Almost sounds like we said it the same way, but this is a different view for sure. Q at 0 is 0 itself, so this is C times 0, resulting in 0. So we connected this end. That's the left-hand side here with this end, the right-hand side, which means we did just show set membership. So we'll say then that shows C times Q is in H. So the last one's done. All we need is conclusion. This shows H is a subspace of Pn. Throw some lazy color coding there. So we've got it, folks. That's how the conclusion goes on this one here. It's a lot of writing. This is when math gets kind of weird in a certain sense. There's not a ton of actual numbers there. It's more just arguments showing how things work, and arguing through set theory is, again, probably the major thing about all this. The more you think in terms of sets and set membership, the easier this work becomes. Well, any questions at all, folks, whatsoever?
time we need to just go through all those three steps or just if we can?
Yeah, if we know it's a subspace, we have to show all three, unfortunately. But if we suspect it would not be a subspace, you just need to find one condition and show a counterexample. Exactly. Other questions about that at the moment? Okay, well, let's take a look at what we've got next going on in the notes. Going down below, I have a couple examples that are going to work with these kinds of function spaces. So here's a pretty interesting one. And after that, this is where it's going to start to wrap up really pretty quickly. Once we get to here, this is the next portion of the problems you're going to see in homework, where we're going to work with theorem 1. I put this in yellow, and this is a pattern I've been trying to copy since chapter 1. Anything that's put in yellow is almost certainly a pretty impactful theorem. And I would consider this to be the most, it's a bold statement, it is my opinion, but in my opinion, this is the most important theorem in chapter 4. The fact that if you take a set of vectors and span them, it is automatically qualifying as a subspace. This is so impactful because what it allows us to do is not actually look at the definition that has 3 parts, which are technical, you have to walk through, but instead, if you could write this as a spanning set, your work is done. If you could write this one as a spanning set, same idea. So these are the last 2 kind of problems in the homework. I felt like we should take a look at a couple more just to get more practice with the core definition. Does that sound all right with folks? Okay, we might not finish the notes today in section 4.1. So if that happens, I'll push the due date like is typical, and we'll come back and finish this one after exam 2. But let's just see where we end up. Here I have a set of functions and C -1 to +1. So probably what we should do first when you see a problem like this is definitely just write that down. C -1, 1. And I wrote that weird, let me fix that. It's C with a bracket, no equalities in there. -1, 1. The bracket is a closed set. C refers to continuity, so this is a set of functions f such that f has domain -1 to +1 and is continuous. You might wonder, why is this set coming up so often? The polynomial spaces seem pretty nice and important, and continuous functions can be well approximated by the right polynomial. But the reason this comes up so often is, if you look at these conditions really closely, a closed set, any closed set, and continuity means what this really is the set of all integrable functions on -1, 1. So every single function that has a possible definite integral is inside this space right here, making it pretty interesting. Now these conditions down below, well, it's a brand new set we're going to take a look at, says we're going to grab these functions that are continuous on -1, 1, all these integrable functions, but assert that they match at the boundary. If we add one extra condition that they were also differentiable, this would be the space of all functions that satisfies Rolle's theorem. It's kind of a curious set in a way. So if you're interested in that, that's the purpose of this right here. That's a subspace of all functions satisfying the actual Rolle's theorem. But our question here is, well, we don't have differentiability. We're just going to determine, is this a subspace of the set to C -1, 1, the same set we defined up here. Okay, so that's the setup of the problem. And again, if we feel like it's not a subspace, we're looking for a condition that's going to potentially fail. But this as a set membership condition doesn't look too bad, really. The zero vector ought to satisfy that. The sum of functions ought to satisfy it. And I don't see how scaling a function would break it either. What could break it is if you said f of -1 equals 5. That's a huge problem already, because now if you take 2 functions, where at -1 they evaluate to 5, add them together, the sum would have evaluated to 10, and you're suddenly out of the set. But this kind of condition is actually not very restrictive, just matching on the boundaries. So let's see if we can run through all parts. It is tedious, but the purpose of it is really internalizing this definition. This is like the 5th time we walked through it. So here's our part A. The very first thing you do is you grab the 0 vector of the larger space V. Just write that in. I know it's down there, but just to emphasize, we need the 0 vector from here. We can say the 0 vector of V equals C negative 1, 1 is, in this case, I think the shorthand is a good idea. I would probably just write it out this way. Z of T identically equal to 0. So here we're saying it's equal to 0 for all values in the domain. So there must be enough context to tell you the domain, but it would be this right here through the context. Z of T evaluates to 0 for all T between negative 1, positive 1. But the moment you say that, we'll say next. We're trying to show that that 0 vector is an H. But if it always evaluates to 0, we can say Z at negative 1 equals 0. Z at positive 1 equals 0. Questions you might have is, why did I look at those two specifically? It's because we're worried about set membership. We have to take that 0 function and evaluate it at the boundaries of the domain, negative 1 and positive 1, and we have to show that there's actually equality. Because it was a 0 function, that's not too bad, right? It's definitely 0 everywhere. So this implies Z at negative 1 equals Z at 1. That more clearly now shows the set membership condition works. And so Z is in H. We showed that step does qualify for the 0 vector. So there's part A. We have to do it a couple more times. But any questions so far, folks, with part A? Okay, starting off again. Well, at this stage of the definition, 2 vectors U and V in H. But again, this is context sensitive. It's okay if you did write it as U and V, but it might be confusing what these objects really are. If you're dealing in a function space, it's probably better to call it, say, F and G. But that could be tricky as well because my set is written in terms of F already, so that could feel like a conflict of notation. It's really not bad if you decide to go that route. It just could look funny on your work. But to avoid the conflict of notation, to make the work look just more clear to get through, let's call what is U and V here as, how about G and H, just the next 2 letters in the alphabet, sort of. So we'll have let G, H be in uppercase H. So the moment we say that, it's a really good idea to write out this property for both functions. Then G at negative 1 is equal to G at 1, and H at negative 1 equals H at 1. So those are the 2 conditions here that follow from set membership. Now what we need to show is you take both of those functions and add them together. We need to show both of those are back in H. So this is our next step. How we do that is we have to show an operation evaluated at negative 1 to start. So let's evaluate at negative 1. Back over here, the function operation goes G at negative 1 plus H at negative 1. And we have to show that's equal to something. But here's our guide. We already know that G at negative 1 is G at 1, so we'll throw it in. Plus, we'll do it again. We know what H of negative 1 is. Well, we don't know exactly. We just know it's H at 1, whatever that value is. So plus H at 1. And here's where it looks a little bit funny. We went left to right to go this way, but we're about to kind of undo it, go in the backwards direction. So if you have a G of 1 plus H of 1, this turns into G plus H at 1, undoing the function operation. And the reason that last step was so important is because the F that's here and the F that's there is now the G plus H. That's just a brand new function, and we think of that as one function. The new name for it is G plus H. So we had to exhibit a function here at -1, and the same exact function right here, but at +1. If we can do that, then we show set membership, and we can conclude that this shows G plus H is in H. So it works, folks. Well, at least so far. We now need to show part C is true, but I have a feeling it ought to be true. I feel like these, again, are pretty technical kinds of things to do. It's all about getting through the set theory. Any questions at all with what we wrote down on part B? Okay, well, that was so fun. Let's try it all over again for part C. See if I can scroll to the right step there. So it starts by saying, grab a vector at H. Now, one thing I'd like to mention about these is there are different styles for writing all this out. And some people feel very strongly that if you've already defined a function G, you've already listed out its property, why should you have to redo that? You might have had that thought when I, in fact, did redo that in some of the problems. So you are allowed to consider this function G to be in the scope of the entire argument you're about to write. We can just reuse it if you would like. If it makes sense to just redefine G down here, you're thinking of the steps more discretely as to separate phases, that's okay as well. But let me go that second approach. I'm just going to reuse the function G that we've already defined and start part C really right here by grabbing a scalar. So let's let C be an R. Then what we have to show is this right here. But what we're showing it for is this kind of function, a C times U or a G times U in our problem. So we're on that stage of the process next. Let's say then C times the function G. So we're referring to this one again. Thinking of set membership, we have to evaluate at -1. Then back down here, we do the function operation and turn it into C times G at -1. The moment we wrote that, we'll go back to when we define G, we mentioned that property. G at -1 is G at +1. So this turns into C times G at 1. Once we get here, what we're trying to get is to this stage. But the way you visualize it is really important. When that says F, we're referring to C times G. We need to make a C times G with a -1, or excuse me, with the +1 look like this. The new function CG at 1 matches up there. So now we have equality for when it was evaluated at -1, evaluated at +1. That means our argument is just about over. We just showed part C is true. That's closure. And if I can get word to work right, there we go. So all we need to say is this shows C times G is in H. And so let's put down just the overall conclusion in one line. H is a subspace of V equals C -1, 1. Definitely kind of an interesting subspace. It could put more structure on it and make it look like Rolle's theorem, but that's how this problem on this one would end right here. Well, these are definitely, again, pretty tricky kind of problems. Any questions or comments at all, folks, on getting through them? Sorry, say again?
Very confusing, isn't it?
I agree with you, yeah. When you go to take a look at these in the homework, one comment I want to make again is, and some people have taken me up on this offer, so I'm glad people are writing, but if you're solving these kinds of problems and you just feel like, man, I don't even know where to start with part 6, or maybe you wrote some stuff down, but you're not sure where it's going, just send me a screenshot of your work or shoot me an email. I'm always happy to help you over email on how to proceed to the next steps, or maybe if there's something missing or anything along those lines. So they are definitely tricky problems. For this section, I'm going to allow rewrite, so if you missed a couple things here, you could lose a lot of credit, but that's okay, that's just learning how it goes. You will have the opportunity to rewrite your 4.1 assignment as well. Well, we're getting through it, folks. On the next block of notes, I took away the definition, so this is where we're just gonna try to do this all on our own and determine if the set of non-decreasing functions on a domain of -1 to 1 is the subspace of that right there. Well, let's not solve this one completely. Let's let this one hang out and we'll come back to it after the exam. But to get some feel for it, it said non-decreasing. What's a non-decreasing function? Well, it could be this one. And now you have to wonder if that's, well, we usually use t rather than x. If that's your non-decreasing function, can you do something to it to force it to become decreasing? In other words, what if you scaled that by -t? You get this function, and that one is decreasing. That means you left the set immediately at that stage. There's no way that this is an actual subspace. So that's the thoughts behind it. The tough part is actually writing it all out. But these last questions go a little bit faster. Well, any questions or comments at all, folks, before we call it a night? Okay, I think this is a good stopping point for us. I don't want to try to write as fast as possible to do a problem in 4 minutes. But other things I want to leave with before the weekend is, if you're studying on exam 2, and if you're going through any of these documents, any of the review material or the one right down below, if anything looks weird, if you're not sure what happened on the solution, don't hesitate to write. I'll be very happy to help out even over the weekend. But have a great night, folks, and I'll see you all next Tuesday. You bet.